Hi, I'm Murray Reeves. I've been doing some work in the past few months on disinfection techniques for coronavirus and came across some useful information on masks. I thought I'd put it together into a package. Hope you find it helpful. Masks in the COVID-19 era. Murray Reeves, 2020. I've recorded this as a presentation with the text for people who can read English a little bit better than interpret what I'm saying. Introduction. I'm no expert, but I am an engineer. We get into all sorts of stuff, and for the past few months I've been studying ways to kill coronavirus. In that time I've learned a lot about the virus and things related like masks. Thought I should share a bit of learning. I'll start with some background on SARS-CoV-2. This is the name of the virus that causes the disease COVID-19, also known as coronavirus. Then I'll talk about masks, how they work, and what makes them good or bad. And finally I'll do a demonstration that you can also do at home if you choose to. Background on SARS-CoV-2. The virus is referred to as a virus particle in the scientific literature. This is a rather scary image you see commonly of the SARS-CoV-2 virus particle. The image on the left is an illustration, and the one on the right is a scanning electron micrograph of a real virus particle with fake color added. SARS-CoV-2 virus particles are about 100 nanometers in diameter. A nanometer is a billionth of a meter, so this is very, very small. For comparison, if you lined up about 430,000 of them, the line would be about the same length as a golf ball in diameter. How do the virus particles get transmitted around? The virus in infected people shows up in droplets of sputum, the word for mucus and saliva. How an infected person's sputum gets distributed around is considered the predominant way COVID-19 gets transmitted from person to person. More about these sputum droplets. Scientists roughly divide them into two sizes, less than 5 microns, which is 5 millionths of a meter, or 0.005 millimeters. They tend to float on air currents. These are called aerosols. Larger, heavier droplets fall to the ground because they are heavy. For comparison, a human hair is about 75 micrometers in diameter. Aerosols can then potentially be inhaled by healthy people, and the droplets that fall can contaminate surfaces. Contaminated surfaces are called fomite. How infectious are these droplets? Well, it may surprise you, but scientists are not too certain about how many ingested SARS-CoV-2 particles it takes to transfer an infection. It's complicated to determine because it takes infecting people to determine this, which is not a good idea when we're still learning about the dangers of the disease. The best guess from other work with viruses like influenza is that it probably takes under 1,000 ingested particles to create an infection. This is just a reasonably educated guess at this time. Calculations show that it's easy to fit 1,000 virus particles in a sputum droplet as small as 2 to 3 micrometers. Theoretically, you could get COVID-19 from ingesting a single sputum droplet that is too small for you to see. If a person sneezes, they project a spray of sputum droplets as shown below. The large droplets fall due to gravity, and the smaller droplets, again called aerosols, are light enough to be carried by air currents for quite a long time and distance. The x-axis below is in meters. A person can also spray out sputum droplets by coughing, as shown below. Not as much as sneezing, especially aerosols. Also, they are not sent as far as for sneezing. Note the approximately 2-meter range where things start to drop off. This is where we get the 2 meters or 2-yard spacing for lineups. A person can even spray out sputum by exhaling. This happens also from talking or yelling or singing or breathing hard during exercise, as shown below. Again, less droplets than from coughing or sneezing, but there's still a spray. What about the droplets that fall and create fomite? It turns out that scientists have observed that the virus particles can remain viable, meaning that they can participate in creating infection, for hours to days depending on the material they land on. The duration of viability depends on other things as well, like temperature, humidity, and sunlight. The good news is that the virus particles continually die off over this time frame. Below you can see the predicted decay of the virus contamination on various materials, meaning the reduced ability to convey an infection by a reduced quantity of virus particles. How does the fomite create infection? If you touch the surface and get particles on your hand, then touch your mouth or nose or eyes, you're conveying the virus into your system. This is why washing or disinfecting your hands is so important. Soap or alcohol sanitizer, alcohol with a concentration greater than 60%, both kill the virus quickly. If you wear gloves and touch your face, the same path to infection happens as with a contaminated bare hand. You should take off the gloves by turning them inside out. You should be careful to not touch the outside fingers or palm of the glove with your bare hand. Now we can move on to masks. There's been some mixed messages about masks and COVID-19 transmission. Part of this is because scientists are uncertain how much transmission comes from aerosol and how much from fomite. Another part of this was a concern that everyone would run out and buy masks, maybe unnecessarily, and there would not be enough supply for hospitals that definitely require them. Masks come in many types now: medical, N95, homemade. A mask provides two functions. In the first case, function 1 I'll call it, the wearer needs it to filter virus-contaminated sputum aerosol droplets in the air near them from being inhaled. In the second case, function 2, it prevents the wearer from spreading sputum droplets to create fomite and contaminate the environment. Function 1, filtration. This really comes down to two questions: how well a mask filters aerosols and how well it fits, meaning are there gaps that defeat the filtering. Filtration efficiency is measured as the percent of particles the mask can filter of a given size. The better the mask, the better the efficiency for small particles. These graphs show the filtration efficiency of various types of masks. For this test, they use salt particles to represent sputum droplets. The salt particles range in size from 0.01 micrometers to 10 micrometers, as shown on the bottom x-axis of the graph. The top graph shows cotton masks. Red is cotton quilt and blue is 600 thread per inch cotton. They both perform well, while the 80 thread per inch perform poorly. The bottom graph shows the difference between silk, 4 layers of silk in green, which is the best, flannel in blue, and chiffon in pink. The top chart here shows the result of multi-layer masks: cotton and silk in green, cotton and chiffon in blue, and cotton and flannel in pink, in comparison to an N95 mask. N95 masks are an industry standard for a factory-made medical mask. You can see for these masks that all the multi-layered masks perform near better than the N95, up to about 0.5 microns of particle size. The lower graph shows the effect of gaps, poor fit of the mask. The experiment compares surgical masks in red, like the blue one below, to a cotton silk multi-layer in blue, both with and without gaps. Both masks show poor filtering efficiency with gaps, around 40% for almost all the particle size. The arrows show where typical gaps are for the masks. Why do multi-layer masks perform so well? It's likely more scientific than you think. The belief is that layers combine two filtering mechanisms. One is mechanical, just physically blocking the particles. The other is electrostatic. Particles stick to the material due to static electric charge. This study, of course, is on salt particles, not sputum droplets, so we have to be a bit cautious on what conclusions we draw from it. What it indicates, though, is that if you wear a good multi-layer mask, or an N95 mask, or a surgical mask, and it fits well, it should filter out 90 to 95% of the droplets, around 0.5 microns or bigger. Smaller droplets might be less than 90% filtered. But didn't we see earlier that infectious aerosols could be as small as 2 to 3 micrometers? This means masks aren't perfect protection from inhaling virus, but they do reduce the chances, especially if you maintain distance between you and unmasked people that are talking, coughing, or sneezing, or even better if everyone is wearing a mask. Recently I was watching Real Coffee with Scott Adams, episode 1055 on YouTube, and he had an interesting analogy. He talked to somebody who said you could represent a mask as a chain link fence and a virus particle as a flea. That didn't present a very positive view of a mask. Scott cleverly said, he thought, because we were talking about droplets and not particles, that it might be better to talk about that flea being on a dog, being hemmed in by the chain link fence. We could add a little bit more to that analogy, say it could be like a flea on a dog, or a flea even on a bird that could get through the fence, but there's 3 layers of chain link fence, all misaligned. Function 2 is contamination suppression. Recall that we showed that sputum droplets greater than 5 micrometers fall from the air. If they are loaded with virus particles, you now have a contaminated surface that can transfer the virus to someone else, again called fomite. We also learned that a good mask with decent fit is very good at filtering the large droplets. This means that an infected person wearing a mask can sneeze, cough, or talk, and the mask will capture the vast majority of the contaminated sputum droplets. As a contaminant suppression, a mask is very effective. Let's do a little experiment to see if this works. Here's the equipment I have for our demonstration. Got a mirror, 2 sides, relatively clean. I have a shield for the mirror. It's going to protect half of it, as you can see. A mask, some water, and Kirkland granulated California garlic powder. That's special. Let's see what that's used for. First thing I'm going to do is talk to the mirror and then demonstrate something that we're all aware of. How much spittle comes out of my mouth when I talk. I have some water for a little bit of moisture. Okay, let's see how this works. Alright, Peter Piper picked a peck of pickled peppers. How many pickled peppers did Peter Piper pick? And you probably can't see very well the spittle that's on there. This is where the granulated garlic comes in. Garlic actually works pretty well for making things smell nice. But it also shows up where the spittle landed on the mirror. So now I can flip over to the other side. I'm going to protect half the mirror again. Place my mask on. And we'll do the same thing. Peter Piper picked a peck of pickled peppers. How many pickled peppers did Peter Piper pick? Granulated garlic. As you can see, the mirror is clean. Of course, if you do this at home, all you need to do is stand in front of a mirror, talk, and you'll see the spittle particles hit the mirror. You don't need to decorate it like I need to do for the video. Okay, experiment 2 is where I try to test out my acting ability. Got my mirror set up again, and I'm going to try to fake a sneeze. Okay. Achoo! Oh, that was really believable. You can probably see that. I don't even think I need to decorate it. Now we'll try to do an equivalent sneeze with a mask. Moisture. Sealed up nice. Okay. Achoo! Pretty clearly better. Hope you found the presentation useful and informative. For me, the outcome seems pretty clear. The mask is going to prevent me from ingesting some particles. It's not going to prevent me from going into a very highly infected space with close proximity with people without masks. But the second thing is it's going to stop me from contaminating the environment that I'm in if I'm actually COVID-19 positive. So if we all wear masks, I think we're all better off.